From our history of the atom, we know that every single electron that is around the atom has a certain amount of energy. The energy of electrons determines the region of space, or the orbital. You'll remember Bohr's energy levels, in which it is found. So the space around the nucleus is divided into energy levels, and the energy levels are divided into things called orbitals. And orbitals are, again, just regions of space. This is important. The electrons closest to the nucleus have the least energy because they're well attracted to the positive charge, and the electrons furthest from the nucleus have a much higher energy. So let's take a look at these things called orbitals. There are s orbitals, p orbitals, d orbitals, and f orbitals. In school, we're only going to study the s and the p orbitals, and we need to take a look at the shape of those orbitals. The s orbital is a spherically shaped orbital. In other words, it is a circle. Not a circle, actually, it's a ball, it's a sphere, so it looks like a soccer ball, and that's a region of space in which the electrons could be found. The p orbitals are dumbbell shaped, or they're sometimes called double teardrop shaped. So they look a little bit like that, and the electrons are confined to that region of space. It's a three-dimensional space. So in class I'll show you some balloons strapped together that will give you an idea of how the p orbitals work. Turns out there isn't just one p orbital though. There are actually 3 p orbitals, and the first one looks like that in the y direction. The second one looks like that in what is called the x direction, because if you think about it, you have got something called the x-axis and the y-axis. So if I had the x-axis, that would be in the x direction, the y-axis. There's also an axis called the z-axis, which goes in and out of the page. And in the z direction, you have also got an orbital going into the page and out of the page. So there are 3 p orbitals in 3 dimensions around the central point of the nucleus. Now, we need to say how these electrons arrange themselves. The electrons are going to fill up the orbitals closest to the nucleus first. You can put 2 electrons into each orbital. They must have opposite spin. So one will spin clockwise and the other one will spin anti-clockwise. The way we represent that in what is called an energy level diagram. Another name for an energy level diagram is an Aufbau diagram. So it's a building up diagram. Aufbau refers to building in a Germanic language. And we're going to take a look at the way we represent that's one electron and that's the other electron. Notice they are half arrows and they are in opposite directions because of the fact that we have got opposite spin. If you have got orbitals with the same energy, for example the p orbital, each orbital in that energy level gets 1 electron before there's a second electron. I always say if you arrived at a 3-bedroomed house with 3 friends, you'd each take 1 separate room before you started doubling up. Draw an Aufbau diagram of sulfur. Now, let's look at sulfur on the periodic table over here. Sulfur has got 16 electrons. So 16 electrons need to be put into the orbitals. The first 2 electrons are called the 1s electrons, 1 and 2. If you can think about it, that's the first period on the periodic table. And those 2 elements, 2 electrons, would be the hydrogen electron and the helium electron. This is your first period, it is your first energy level, and that is the s orbital. The next one is, and now I need to show you something, this part of the periodic table is called the s block. This part of the periodic table can be referred to as the p block. Out of interest, this is known as the d block and that's known as the f block, but as I just said, we're not doing the f and the b and the d orbital. So worry about the s block and the p block. You only need to be able to do Aufbau diagrams for the first 20 elements, in other words up to calcium. Now, the second energy level is the second period. We have 2 electrons in the s orbital, and then you have got an additional 6 electrons in the p orbital. 1, no, look what I'm doing now, 2, 3. I first give each orbital 1 electron before I continue 4, 5, 6. So how many electrons are there in that second energy level? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So notice how the Aufbau diagram correlates almost exactly, well, it does exactly, to the periodic table, except that the periodic table is going horizontally here and the Aufbau is building up. Now we go into the third energy level, 2 in the S and 6 in the P. 1, 2. But we're not going to all the way in 6 in the P for sulfur. We're only going to 4 in the P. 1, 2, 3, and now I add another one, 4. That is an Aufbau diagram for sulfur. If I was going on, I would, to let's say calcium, I would then say, put the next 2 electrons in there, and then 1, 2 in what is called the fourth energy level. So this third energy level is exactly the same as the third period. The second energy level, the second period. The first energy level is the first period. And then the fourth energy level is going to be the fourth period on the periodic table. And you only need to know the first 2. So that's the end of that story. I want you to... Now this is an energy level diagram thing that looks a lot like the periodic table. So we've got period 1, period 2, period 3, and period 4. You are now going to fill this in. You can either take a screenshot from this video, you can go onto Google Drive and grab the notes, which have got a blank page. But you need to fill in your own version of this. I'm going to fill in 1 or 2 just to show you how to. So let's say potassium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. That's potassium. Notice that it is in the fourth period and therefore it has the fourth energy level electron. If I were to take sodium, it's in the third period, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the second period will be filled, 11. If I then take lithium, I go 1, 2, 3, that's it. Second energy level only has 1 electron in it. If I go on to hydrogen, 1. Now what I want you to notice about those is that they have got exactly the same number of electrons in their outer energy level. Now the outer energy level is the last energy level that's been filled in each case. So in hydrogen it's the first, in lithium it's the second, in sodium it's the third, and in potassium it is the fourth energy level. Notice 1 electron, 1 electron, 1 electron, 1 electron. What do we know about this? This is group 1. It has 1 valence electron in its outer energy level. So we're going to see if any trends develop in the rest of this. I want you to press pause now. Complete the rest of this on your own. Show it to me before you unpause or start the video over again. So, if you take a look now, group 2 in its outer energy level has got 2 electrons in each case. Group 3 in its outer energy level has got 3 electrons. Group 4, notice that these look exactly the same in their outer energy level. Group 5, exactly the same in the outer energy level. Group 6, exactly the same in the outer energy level, second energy level, third energy level. 7, second energy level, third energy level. And then we go to group 8, which has got 8 electrons in its outer energy level, if you like. You can also see it as having no electrons or a full electrons in the first energy level, full second, full third. Helium's obviously a little bit of an anomaly. It could have been in group 2, but it also has a full first energy level, full second energy level for neon, full third energy level for argon. That is why the noble gases do not bond, because they have already got a full outer energy level. So here's just a little summary of what the outer energy level looks for each of the different systems. Group 1 elements have got 1 electron in their outer s orbital. Group 2, 2 in their outer s orbital. Halogens in group 7 have all got 5 in their outer p, but don't forget that the s counts, so that's 7 altogether in the outer energy level. Elements in the same group have the same outer electron arrangement, and that is the key, and that is why elements in the same group have similar chemical reactivity. Pauli's exclusion principle, you need to learn these exclusion principles, and Hund's rule says any orbital can contain a maximum of 2 electrons provided they have opposite spin. That's exactly what we've been doing along the way here. Hund's rule, each orbital in a sublevel is first occupied by 1 electron before a second electron gets added into that suborbital.